All right, so what we're going to do for the next part of this session is actually go through a rather straightforward but soup to nuts modeling activity that models the column of water that's falling. And this involves a little bit of physics, and sometimes if you teach in liberal arts settings, students get anxious about that. We understand that. But at the same time, it's sort of self-contained and we can bring them along in that. So it also involves collecting data. And if we finish with that one, we'll take a look at a slightly different model. All of this material can be found at our website. Just for the record, this is what the website looks like. And what we're looking at is a bunch of things, and they are listed in the resource guide under sort of like table of contents in a textbook, first order, second order, non-homogeneous, and so forth. And now I have to figure out how to get back to my screen. And just forgive me for a second. There we are. And both of these are examples of what we call modeling scenarios. For each of them, there's a student version and there is a teacher version. The student version, I'll click on that, is right here for this one. And what the students would be able to see is this, in this case, short description, which has a statement of the problem and perhaps a little background. This one happens to have 11 pages worth of material, including the derivation that we'll go through. And it has lots and lots of information. Okay, so if we go back to our slides, we could see a teacher version of this. And I'm putting this up again before we start because I wanted to point out to you that there are maybe 8 or 10 modeling scenarios that are in SIMIODE that are in Spanish. And these were translated by Migdonio Gonzalez from the University of Panama, the Technical University, when I was doing a workshop there. And so you'll see them all. In fact, if you just search for Spanish, you'll find all of the ones that are there. These are links to videos where we'll be collecting the data, and this is in the student and teacher version. And the teacher version has additional materials, data sets, an Excel spreadsheet that we'll access shortly. So let's get on with it. What the students are going to do through this is they're going to see and collect some data. They're going to conjecture an empirical model. They're going to try to build an analytic model with some principles that we're going to develop and build that differential equation and solve the differential equation. Now, frankly, you can use this even before you get to the technique, which is separation of variables, as a motivator for why you would want that technique. Or you can do this post the technique, namely, we've now learned how to separate variables. Let's see if we can apply that in the context of some model. And then finally, we're going to estimate the parameters. In this case, there's only one parameter in the model. And we're going to compare the model to the actual data and see how good our modeling efforts have been. So if you would like, you can go and just type in SIMIODE YouTube if you want to leave, but I'll do it for us in general. And what we're looking at is a video that has sound on it, which we don't want. And this one video is one of many. And what it'll allow us to do is, and all of this is explained underneath in the paragraph in YouTube. And this is a configuration where we have a 2-liter bottle of dyed water. And we have a digital clock. And the hole that's bored in the bottom is 11/64 inches. It's done with a Black & Decker drill bit and a column for measuring the height of the water is here. You can do this yourself. This happens to be done by me, and there are other onlines that you can get. But this one, you can have it all, and you can start the video, and you can read the clock to the nearest thousandths of a second. You can step the clock up and sample from various points. You have to decide where you're going to read the height. This is this bow or meniscus. And if you want to read at this top line or the bottom of this, but be consistent, and you can take as many samples as you want. So students can do this. There are different diameter boreholes here. Obviously, the bigger the borehole in the bottom, the faster the water is going to exit. And so different students could take different configurations. And what I want to do is get out of this, and I can't seem to, yeah, there we go. I beg your pardon. Forgive me, I lost, yeah. I lost my, my screen sharing. Oh, here it is. Excuse me. And we'll get back on track here. So what I did was I went to that site some time ago. I collected the kind of data you would get, in this case, 2, 4, 6, 8, 9 data points. The clock on there has to kind of be zeroed out. So the clock starts at some time, and I made that time 0. And I sampled at various times throughout the video, and I found out the various heights. And I opened up a spreadsheet that I'll share with you, and I plotted the heights. There's good news. The height goes down as a function of time, okay? It goes down, it's hard to say, but it has a little bit of a bow in it, but maybe a straight line would be a good model. Namely, height as a function of time could be linear. And we look and we see that it has a bow in it, and a straight line doesn't. So maybe we could try a function with a bow in it that might model sort of the dropping of that. And the natural one might be to fit exponential decay. What I'm doing here, and we'll look at it later, is the actual fitting of selecting various models inside of Excel. And it's giving me the parameters. I'm not printing them here, but it looks like straight line, it bows too much, and the data bows too much, and the exponential decay, it looks like the data isn't bowing enough, or that is, the model is bowed too much. So we could just try to fit more curves. In fact, you could try a parabola, that 4th, 5th, 10th degree polynomial, none of which have any real physical meaning. So instead of doing that, what we're going to try and do is ignore these empirical models and see if we can't come up with something that has a little more analytic physical basis to it. So we look at the data again, and since we're in a course in differential equations, I'm going to try to find out how fast and what is the rate of change. So maybe we could just take a few rates of change. Over the first interval between 0 and 2.187 seconds, we see that the rate of change of height with respect to time is a loss of about 0.2286 centimeters per second. We see later on, towards the end, that the rate at which the height is changing is slowed down. It's down to about 0.122 centimeters per second. And if we go back to the data, we see that in the beginning, it's falling a little more rapidly than it might be towards the end. It's not so pronounced, but we could convince ourselves that this fall is less rapid than up here. So we bounce back and forth between some arithmetic and between the actual data that we have. So what we're going to try and do is use a principle that was developed by Evangelista Toricelli, who was a student of Galileo's. And he's known for having invented the barometer. And I like his mustache in this picture and his attention to fur. What I'm doing here is conducting a workshop for my fellow teachers, but I'm trying to give you a flavor of how you might develop a lesson around this. There are two ways you can do this. You can give them Toricelli's differential equation, which is what I've done here, or you can hold off on that and sort of build it from scratch, which is what we're going to do momentarily. So I've elected to pose the end differential equation right up front for students and for you and say, this is where we're going to go. And we're going to figure out where on earth Toricelli got this and how he got this. And then we're going to use it to model and do some things. So what this does, if you say it out loud, is it says the rate at which the height changes is minus b, some constant, times the square root of g, which is the gravitational constant, times the height. And if we look at it, we'll see that when the height is big, the square root of height is big. So initially, when the height is high and we have lots of water, the rate at which the water is falling is big. When height is very small, then the rate at which the water is falling is very small. And that makes a kind of an intuitive sense. Anytime you do a model, and I always tell this to my students, you want to do a little reality check right away and throughout. So we're going to build this differential equation from first principles. And the first principle is called the law of conservation of energy. And some of us haven't taken a full-blown physics course, or if we have, it's been a while. And there are lots of energies that mass and particles have. They have a charge, they have atomic energy, they have thermal, they have heat, they have light. The ones we're going to look at are more about mechanical, and that is so-called potential energy. It has more potential energy when it's higher than when it's lower. And kinetic energy, that's depending upon how fast it's going. So when it's going very fast, you have a lot of kinetic energy. High-speed accidents have kinetic energy. Fender benders at stop signs have low kinetic energy. So here's some equations, and we're going to try to explain them and why we're doing this to build our model. And what we've got is that we're going to measure the total energy of a slab of water when it's at the top. And we're going to measure the total energy of the same slab of water when it's down at the bottom near the exit borehole. So the initial, or at the top, TE sub I, is the total kinetic energy plus potential energy. And I'm going to give you some formulas that physicists have derived to measure these quantities. The kinetic energy is 1/2 the mass of that slab of water times the velocity initially squared. And so what it says, if you have more mass, you have a lot more kinetic energy. If I hit you with a car versus with a wad of paper, you get a lot more kinetic energy. And if I hit you with a high speed, VI is big, you have a lot more kinetic energy. Plus the potential energy. And the potential energy is just the mass, the amount of stuff you have, times the acceleration due to gravity, times the height. So if you were to conduct this experiment on Jupiter, G would be very, very great. If you were on the moon, it would be much less. On Earth, it's about 9.8 meters per second. The mass, or 980 centimeters per second. The mass would be given in grams, and the height would be given in centimeters. So initially, we're going to release this object. It has zero velocity, hence zero here. So the initial total energy is at zero kinetic energy plus all of its energy is in potential. It's just mass times gravitational acceleration times height. Now for the final energy, when that slab of water is down at the bottom and it has height zero relative to the borehole, it doesn't have any potential energy. It's shot. But it has picked up a lot of kinetic energy. And so it has a higher velocity. The mass hasn't changed, gravity hasn't changed, but it isn't involved in this expression. So what I have is the total initial energy is just mgh. The total final energy is just 1/2 mv squared. And the conservation of energy principle says the total initial energy is equal to the total final energy. So that says that the mgh term and the 1/2 mv for the final velocity squared term are the same. You'll notice in this expression, we can divide through by the mass. And what we'll have is if we multiply through by 2, we'll have that the final velocity squared is the square root of 2gh. And if we actually solve for that final velocity, we will find out that that final velocity is minus a constant times g rooted and h rooted, okay? So this constant that we are interested in is something to be determined by the nature of the physical configuration, the circumference, maybe the friction of the borehole, the nature of the fluid. Is it 1040 motor oil? Is it sludge? Is it slime? Is it liquid? So that's the constant that we're going to determine. We're going to assume we know what gravity is where we live, and we're going to try to solve this differential equation, use the data, and try to determine the constant. So here is a review of separation of variables. Or for some, it may be the first time, and you have to decide how you want to go about doing this. Do I want to take time aside right now? Or do I want to just refer to a previous lesson? So these are the common steps. And here you integrate both sides and you get that constant of integration. And that's very important because that's going to be, as you well know, the way you express initial conditions. And that's what we're doing here. So this is the analysis that we might go through to get close to equation 1, which says we now have converted from a differential equation to a closed form solution for the height, which involves 3 things. This parameter we don't know, g, which is acceleration due to gravity, which we do know, and the initial height of our slab of water, which we do know from our data was 11.1 centimeters. So if we put those numbers in, we get equation 2, which looks like something that's reasonable. It says the height is the square of this expression with a constant or parameter b unknown. And remember, this is for this cylinder on this data that I collected. It's going to be different from other cylinders and other data. So we have our model and we seek to determine the parameter b. Throughout the courses that I've taught over the years, we've done this whole approach of build a model, have some data, either we collected it or we got it from an article. There are lots and lots of sources, and at SIMIODE, we give you lots of sources for articles. And what we do is we take the difference between the data and our model. This is a very messy expression. This h sub I is a number. This is that formula with the initial time number put in. And so this is a garbagey mess. And what we want to do over the 9 data points, we want to find the parameter which minimizes this sum of squares. Students in science classes have been used to least squares techniques. There are certain words that you can say that trigger their salivary glands. And if not, then you have to kind of introduce it. And I will do it here with you in a spreadsheet because it's most easily seen. I've identified here all of the variables in these expressions. And that's always important that you do that as well as units. So here's an example from an Excel spreadsheet, and we're going to go live to the Excel spreadsheet in a moment. But this is a screenshot. This was done 6 years ago by me. I tell you the video that we got the data. This is our model. H prime of t is equal to minus b, the square root of the expression g h of t. And this is our model solved. I just wrote this in there for reference. This was the time that we took off of our data, and this is the time that's zeroed out. So 8.679 seconds according to the clock on the video. I'm going to call that time 0. This one is 2.187 seconds later, etc. And here is the timed observations that we got. With this parameter, b is 0.002, kind of arbitrarily picked, but you can play with it a little bit to get reasonable numbers. This is what our model says, and this is what the actual height is. This column represents the sum of the square errors, the difference between the actual and the model, and it's that difference squared. And so what we're doing is we're adding that up, and this is that number, which is the sum of those messy, messy, messy equations. And it's saying that so far for the parameter of 0.02, we have a sum of squares, which is 7.679. That's not as helpful as this picture. Let's look at this picture. The picture says, our model says in red that the column of water does fall, but our model doesn't seem to be falling as rapidly as the data. So when we get to the live Excel, we're going to play with that model by changing the parameter. Okay, so this is all set up in the teacher version, and you as a teacher can either elect to share this with your students, have them build their own, sketch out the beginning and maybe only give them this much information and ask them to put in their data, any combination of this that you're comfortable with. So this is the final result that I'll get to when we do a live one here. And what you see is the red dots are the model and the blue dots are the data, and they seem to be right on. So let's go to a live Excel sheet, and we'll do that by going to this sheet, which I thought I was going to, yeah, here it is. And I'm going to make this bigger. So we're looking now at a live Excel sheet that is in the teacher's version of this modeling activity in SIMIODE, okay? And here again, you see the same sorts of stuff that I alluded to before. You can see the typo that I put there 6 years ago and still haven't corrected with the word with, an extra I. But here's the model. Here's the model differential equation. Here's the model itself. Here's the data that we have about time, and here's the actual data. Here's the sum of the square errors. This is the estimate of the parameter. This is a narrative for you, the teacher, to explain how to use Solver. I find that when we do these workshops, a good number of teachers have never experienced Solver inside of Excel. And it is a powerful tool, and I'm about to show you how powerful it is. So remember I said before we could try some values of this parameter, and I could plug in, say, 0.003. And what this is saying is we're making this number b very, very small. What it's saying is the rate at which the height changes is very small over time. And so our model doesn't drop off as fast as our data. We could say, let's make the rate at which it drops off very large by comparison. And what happens is things get way distorted, actually, because it's parabolic. It drops off and picks up. That's a bit scary. So let's go back to what we had originally and say, okay, Excel, I could play all day with this and get better and better and try to minimize the sum of the squares. Or I could actually use this powerful tool whose commands are here. Let me just go through what the solver is going to do for us. It's going to take the objective cell, which is in yellow. It's going to say the sum of the square errors is what I want to minimize. That is my objective function in linear programming terms. And the parameter that I'm going to play with is parameter B. And it's in cell G10. The dollar signs are Excel's way of saying no matter what happens, always go to that cell and take it. So these are the commands. And what I'm about to do now is actually execute them. So the way you execute them is to go to data and over to the right, far, far, far to the right, there's a little word that you can see that says solver. And what I'm about to do is engage the solver, and you will see it come up with a small window. This is an active window. The one that's in the background there is just a dummy to show you how it looks. And you're going to have to watch this very closely and pay attention, because I'm going to tell it that what I want is, I want you to find the minimum sum of the squares in terms of the parameter B. That is, find the parameter B, which makes the sum of the squares minimum and which will make these two graphs much closer. When I hit this solve button, look at the graph on the lower left. Watch it. What you noticed is it almost looks like one of the graphs disappeared. And indeed, that's what students will say. But if you look carefully, you will see there's a red dot and there's a little faint blue dot behind it. We're seeing the red model and the blue data are spot on. Another thing to notice was, remember with our original parameter of 0.001, we had a sum of square errors of around 7. Now the sum of square errors is around 0.01. And all of these differences are within 5/10,000ths. So they're all very close. So our model is a nice fit, and we have a parameter for our particular, and by the way, I'm going to accept that. If I don't, I can redo it again. But what we have is a model, and I have my parameter for my particular configuration of 11/64 diameter for the drill bit that drilled that hole. If you picked a different video, you would get a different parameter. Obviously, a smaller hole, you're going to get a smaller parameter. And so you might have students do different videos to get that, okay? So I want to go back now to that last thing we just did, was to jump there and to point out, kind of in summary at this stage, that in a traditional course where techniques are primary, oftentimes the differential equation that we saw may have just been presented without any background, without any substance. And what we did was we tried to motivate why that differential equation even occurred, and then what strategies might we use from what we learned previous as a solving strategy, or what we're about to learn as a solving strategy. I prefer to do the latter, namely build to a differential equation and say, what on earth could we do now? And refer to simple calculus, separate the variables, integrate or anti-differentiate, and lead that in maybe as the first example for separation of variables. So what we're trying to do in SIMIODE, and what I've been trying to do here with you, is to motivate by modeling. So here's a class assignment. Oftentimes I ask the students to summarize what we did in class, rather briefly, but take some time, and I usually leave them with this material so they don't have to take notes. Summarize going from first principles, not all the details, just the highlights to get to this differential equation. Go collect the data if you haven't before class. Sometimes you tell students before class, go to collect this data and bring it to class. You can take as many data points as you want. Some people will take 50 data points and some will take 3, 4, 5. I took 9. Try and see what happens. So here's what we do in Excel. This is an outline of that Excel. And what we are doing here at the bottom is trying to collect data for different parameters for different configurations from our class. So this is what we've done. We've collected the data. We've modeled the phenomena with a first order nonlinear ordinary differential equation. By the way, you may introduce those terms for the first time in this setting if you haven't done what a traditional DE book does, namely classify them all before you even get to them. We've solved the differential equation using a technique we're going to use repeatedly in this class called separating of variables. We've determined the best parameter by minimizing the sum of the square errors, so-called least square errors. And we validated the model. First of all, we validated it visually. Secondly, we validated it by pointing out that it's the least sum of the squares. And we're trusting our physics. We're trusting this principle of conservation energy. The physicists call it laws, and rather than just empirical fitting. And then we're communicating the results. So that's the end of this first presentation. Any questions, conversations, because we have more time because we don't have a session following us. So anything, just unmute yourself and speak up. I see we're a quiet bunch. That's okay. I know some of you and I know you're not quiet, but that's fine. Okay, so we did this, and it's one of many scenarios. And since I knew we might have some extra time, I prepared yet another one that you might be interested in doing. And it is a 2-compartment model, and it has 2 parameters. And again, I want to show you that this is inside SIMIODE, and this is the student version. And if you click on this, the student will have a printout that they can print or just use in class. And they can scroll down here and they can see background. There's only 2 pages of this. And here's some data. And what we're going to try and do is model the amount of LSD that's in the tissue portion of the body by just knowing what's in the plasma, namely in the bloodstream, because we have an IV and we can sample the concentration in the plasma, okay? So this is a student version. The teacher version has quite a bit more background. This version is available in Spanish as well. So let me just go to the highlights for what's in this model. Here's the data. This was done in 1969 and written up by Carl Metzger, who was a chemist at Upjohn in Kalamazoo, Michigan, and early programming to do pharmacokinetics, that is the study of kinetics in pharmacology. And in this case, these were studies for students done in Harvard. This was independent of Timothy Leary, who was also doing studies. And this data was 5 students who volunteered to come in and basically drop some acid. I'm sure that's not what they said, but they were infused with concentrations, and all of this is outlined in the paper that Carl has published, and you can look up. And what we have is everybody had the same amount. They all have slightly different body weights, but this is the plasma concentration in nanograms per milliliters after about 1/10 of an hour. So subject 1 had 11.1 nanograms per milliliters. And they gave them an arithmetic test. And they gave them these problems and they recorded their scores. The idea was that the more and more influence you were under the drug, i.e. were stoned, the less likely you were to accomplish on these tests. So some of these youngsters, you can see their test scores are decreasing as the drug begins to move from their bloodstream to their tissues. We build this simple model. There's more than you need to know here for this short conversation. But basically, we infuse into the plasma, that is the bloodstream, a certain amount of this through a plug infusion. And we can, through that same portal, we can sample a bloodstream and later then analyze the concentrations. What we're really interested in is how much of this stuff is in the tissue. Now, there's lots of tissue in the body, but we're basically interested in the cranial and what's happened in the brain. So this is an example of a two-compartment model where stuff comes in and stuff goes out through discrete excretions and other things like the kidney absorbing stuff. But some of it does cross into the tissues of the body and come back out as it's expended. And we build a two-compartment model where we have the rate of change in the plasma and the rate of change in the tissues. And these all depend upon volume times concentration. You always have to be careful on what you're doing, whether you're doing volume or concentration or mass, and make sure your units are right. These constants can absorb a lot of units, but you got to be sure that the terms you're adding up here are consistent. So we have this system of differential equations. It's a linear system in the concentration in plasma, CPT, and the concentration in tissue, CTT. And we can look carefully at it again, and this is a system with symbols all over the place. And I was using Mathematica at the time, and I'm giving you a sample of what the output in Mathematica looks like for the concentration in plasma with all of the parameters, K sub A, K sub B, and K sub B in it. And it goes on and on and on, a page of formulas. Okay, so this is our solution in terms of the two parameters, I'm sorry, the three parameters, K sub A, K sub B, and K sub E. And what we want to do is we want to find the sum of the square errors between our observed data and the model. This is an unbelievable mess because the formula for each one of these entries, and there are 7 of them because there are 7 observations, the formula for each one of these is a page long. The sum of the square errors is a page minus the data and then squared and then added. So this is an enormous output on a Mathematica screen. But you can use a find minimum command. You can't plot this surface, the parameter surface, where the sum of squares is a function of 3 variables, because we don't live in 4 dimensions. But if it was a function of 2 variables, you could get the parameter surface and look at it. So after we find the best fitting parameters in Mathematica using the find minimum command, remember in Excel, it was solver, and you could do this in Excel as well. You just got a massive formula you got to worry about. Anyway, so we get the best fitting parameters, and here you have the final result, which is rather remarkable until you realize this is a human subject, but this human subject is not a social science. This human subject doesn't have any discretion. This human subject's body is working not as clockwork as the water falling, but pretty consistent in terms of its modeling, its physical behavior. So what you get is your model with these parameters, and the kineticists want to know these. This is the kind of data that the pharmacology people know when they say take one every 4 hours versus take one every 2 hours, because they need to know the staying power, the release. And they can change these parameters if you look up the literature in pharmacology by putting coatings, by putting inhibitors, et cetera, et cetera. And they'll say take with food or take without food. So there's lots and lots in pharmacology and pharmacokinetics, and this is just one. So here, for the record, is the final best fitting curve that models this. Here are the parameters, and the ultimate evidence for many of us is this picture that says this model, this messy linear system of equations solution is really, really quite good. Even better, what we can do is, if we know that parameter, we can plug those parameters into the concentration in the tissue, and we can actually predict what the concentration in the tissue of the body is in nanograms per milliliters. And this is in terms of hours, from the time of ingestion of this LSD to the high point of 6+ nanograms per milliliters only took about 30 minutes. So what that says is, this is an example of what it means to get high. And basically it's saying you can see that the tissue levels of LSD is highest here, and it decays throughout time. So that that's quite natural. After 4 hours, there's not much of a buzz. I've never done this. Unlike Bill Clinton, I didn't even inhale. So I'm not experienced with this, but after 10 hours, there's hardly left. And if you think of painkillers or drugs that you take for thyroid conditions or whatever, they do the same thing. They peak and then they dissipate. What the multiple drug doses are is they want to give you a dose somewhere where it's at a low threshold and it'll peak again without overdosing you. So I found when I first learned about this model and did it, and I had Carl Metzger come to the college I was teaching at from Upjohn and give a lecture on this back in the 70s. That's how I learned about it that long ago. I was amazed that you could learn what's happening in the tissues by simply sampling what's happening in the bloodstream. And I guess I was naive, but if you believe in these models, then you can take for sure that this is what the tissue has without sampling the tissue. We don't have a cranial implant. We are not taking the tissue samples out of some organ in the body. We're just sampling what's in the bloodstream, and from that we can tell what's in the tissues. You can, of course, do that in certain surgical procedures if you want to know the thyroid capacity. Often the thyroid absorbs iodine, and you can put a probe there for that, but that's really drastic, and so maybe you just use some models like this. By the way, here's the plot of the concentration, of the test scores versus the concentration. And all of the concentrations show you that as the concentration increases, the test scores tend to decrease, which is a strong affirmation that this drug has the effect of debilitating our ability to do at least simple arithmetic skills. The advocates of the drug would tell you doing those skills is nothing compared to the Pandora that you're going to experience when you do the drugs, but I'm not in the drug sales business. So, but what it really means is for every nanogram per milliliter that you increase the tissue concentration, you drop your your scores by about 9 points. Okay, I'm going to conclude this presentation, and again, I'll turn to you and ask if there are any questions or comments or observations you wish to make. I see we have 3 colleagues left in our group. And
hi, Brian.
Yes.
Good to see you. This is Boyan.
Yes, I see you from New York. How are you?
Hi. I was actually wondering, do you have data also posted on the SIMIODE for these modules, the projects?
Yes, for this one, we only have the data that was available in Carl Metzler's paper. We have other activities that do have the data. For example, we have one on ophthalmology. When you get a surgery, they inject a gas to make the retinal region empty of fluid. And we have hundreds of patient data that was all anonymous, that was given to me by ophthalmologists at Yale University. Some projects have more data than others. Some have pointers to reference data. So for example, their data is in physics journals. Oftentimes physicists are interested in terminal velocity. But we might be interested in the differential equation that models the full path of a projectile. So we can use their data to do more than a terminal velocity. And those are cited in the references for some of them. And some of them have videos where students can collect the data. I made one where you have the spread of slime, what teenagers do. They make slime with flour and some stuff, and then you spread it out on a table, and you can model the spread of that, or you can just model anything you want like that. So we have videos that you can take the data from. We have data in a good number of them, that are part of what the student can get as well, not just the teacher. And we have articles that have pointers to the data. So, and Deb Hallett, our first keynote speaker, is going to be talking about data in differential equations and sources and what her project is working. So there is data, and some are lean on data. And by all means, if you start collecting data, we'd like you to add it to the resources.
Sure, thank you. I assume usually it's an Excel file, right, or comma separated?
No, it may not be. But yeah, yes, quite often it is. And incidentally, while I tended to use Mathematica more in my teaching career, Excel has visual prompts. You can compare columns. And there's a certain thing about looking at columns of data versus a list of data. You can plot it immediately, you can difference it. And so Excel has a comfort level for many students. They may have used it just to keep track of personal finance and so forth. So often the data is given that way. Sometimes it's just given as a text file with delimited commas. But Excel tends to be, as Boyan suggested, one of the better ways. Okay.
I'll try to convince you today that R is the new Excel.
Yes, Boyan's going to give a tutorial on RStudio, and so we have an advocate. So I'm going to stop the sharing, and I'm going to stop this because we're going to move on at 1:30. I'm sorry, we can keep talking, but at 3:15 Eastern Time, we will come back and have our first keynote in the main room. So you're welcome to join us then.